Hi, thank you for tuning in to my second installment of Chemistry Cheat Codes, a series where you get to hear advice from a lab TA on chem lab success. This episode will be dedicated to Experiment 2, Chemical and Periodic Properties. The Chemical and Periodic Properties lab typically involves students going through many different reactions and recording their observations. At a certain university, you might be asked to do things like test substances for their acidic or basic properties, measure the conductivity of substances, or even watch highly reactive alkali metals like sodium or potassium interact with water. What happened in my lab last year was that the students ran through all of the experiments and then went home to answer the post-lab questions and ended up being completely lost on the purpose. In Gen Chem Lab, you can usually attribute the purpose of the experiment to one of three broader themes, them being experimental design and error analysis, critical thinking, and technique execution. The purpose behind us making you do all of these tests on various chemical properties is to stimulate your critical thinking skills. This lab is big on seeing if students can put their observations together with their chemistry knowledge to come up with an explanation for what they saw in the beaker. Remember from the first episode, the goal of science is to explain. In this case, you're explaining what happened in the beaker. Now, this is your second week of lab, so you're not supposed to have that much chemistry knowledge. It would be totally impractical for you to memorize all of these chemical properties and trends before you came to lab to be prepared. Lucky for you, all you need to be able to do is read the periodic table to ace this lab. You could just try to memorize trends, but honestly, that makes no sense to me. Let me show you what I mean. Honestly, this is something I wish I was told earlier before I did this lab and countless other labs. You're going to be asked this question in the post-lab. Explain any differences in conductivity that you observed. Do you see a trend on the periodic table? Explain this trend. That last question is the killer. Explain this trend requires you to dig into your data, match it up with the explanation for the data, then makes you dig deeper and asks you to essentially make a prediction. Give a reason on the molecular level for what you're observing. The trend is not that hard to figure out, but you need to know the right thought process to figure it out. So I will give you a much harder example and show you how to derive the answer. Let's tackle the trend of electronegativity decreasing as you go down a column. This is an interesting trend because you can actually use some very simple electrostatics to figure it out. Let's say we did an experiment where we observed fluorine reacted more violently than did chlorine, and the post-lab asked us to explain why fluorine reacted more than chlorine and then explain this trend that the experiment revealed. On the surface, we can remember that extremely low or high electronegativities produce the most reactive elements. In other words, we are predicting to see that fluorine has a higher electronegativity than chlorine because that would confirm our observations. It turns out that fluorine has the highest electronegativity of all the elements at 3.98. and chlorine is sitting at 3.16. We can then answer the beginning of the question. We can say that fluorine reacted more than chlorine because fluorine is more electronegative. This means that fluorine has a greater propensity to pull electrons towards itself, which allows it to initiate a chemical reaction more readily than fluorine could. Now onto the beast. Explain the trend. We are looking for you to dive deeper here than just identifying the trend like you did before. Now you need to use chemical theory to make your case. Let's introduce Coulomb's law to first begin to answer this question. Coulomb's law is an equation that states the electrostatic force between two charges is proportional to the two charges multiplied together, all divided by the distance between those charges squared. This is written out as electrostatic force is equal to Coulomb's constant multiplied by the first charge multiplied by the second charge, all divided by the distance between them squared. This law will help us explain the trend. Let's look further into what this says. First, it is useful to think of electronegativity as the force that the nucleus has on the electrons in the valence shell. Think back to the first episode. This is a model that I am using to answer this question. Is this approach perfect? No, it is not. If I was a quantum mechanician, I would be using a far more robust and accurate model to explain these trends. However, I am a student of general chemistry, so this model will suffice for my purposes based on my analysis on how my assumptions hold up to the real world. I know that a force is a push or a pull, and I know that electronegativity is a pull of sorts on the electrons. So I will model electronegativity using electrostatic force. When we look into Coulomb's law, we can actually plug in a value here, which is one of the charges. One of the charges will be the charge of a single electron that we are going to say is the electron that the element will take in order to complete its valence shell in a chemical reaction. So the only things that are really varying in this equation are the second charge, which will be the charge of the nucleus, and the distance between the nucleus and the electron. It should be evident that in this case, the distance between the nucleus and the outermost electron plays a more dominant role than does the charge itself. You might notice that chlorine has more electrons than fluorine. In fact, it has a whole shell's worth more. That is going to put those electrons out quite a bit further than for fluorine. So there's our explanation. We can finalize this analysis into this succinct answer. The trend of electronegativity decreasing down a column was evidenced by fluorine being more reactive than chlorine, and can be explained by use of Coulomb's law. Coulomb's law states that F equals kq1 q2 over r squared, showing us that the distance between charges plays a more dominant role than does the charge of the nucleus, as the charge of the nucleus is a linear term in this equation, and the distance between the charges is a squared term. Since going down the periodic table has elements increasing in atomic radius, as more electrons are populated in outer shells, the electrostatic force on these electrons is typically less. Thus, electronegativity should decrease going down a column. This process is far more involved than the one we are going to ask you to follow, but you should start trying to think like this, especially during this lab. Look for the chemical reasoning, the chemical theory, as to why certain trends are the way they are. If you're always looking into the chemical reason, you will find lab to be entertaining and chemistry to be fulfilling. Don't get lost on the purpose. Stimulate critical thinking skills. This has been Chemistry Cheat Codes, Episode 2. I hope you enjoyed this episode, and I hope you join me next time for Episode 3, The Rocket Lab.